day of our opening weekend for the Art of Planetary Science 2020, the virtual Odyssey. We're very honored to be kicking off our Sunday, a little bit of play on words for today's Sunday event, to actually observe and talk about our own star, the Sun. So we are pleased to invite one of the main sort of outreach functionaries and telescope groups within the Tucson sphere, the Tucson Amateur Astronomy Association, which has a rich history going back into the 1950s, actually starting out as a group of satellite watchers, but has now evolved into several telescope owners, astrophotographers, and members of the public who come together to come to events such as the Art of Planetary Science. You might have seen them around at different schools or different public spaces around Tucson, or even on the outskirts of Tucson in their dark sky location, running public events and star parties. And of course, in lieu of a physical star party, or sun party as it would be today, we're going through our virtual Zoom sphere here to observe our star, the Sun. So I'd like to introduce Jim Knoll, who's going to talk about our Sun, our star, and a little bit about TAAA beyond what I've introduced. And welcome. Thanks for joining us.
Yeah, thanks, Allison. So yeah, welcome everybody. Normally what we would be doing, like last night, we would have participated with a large international Observe the Moon event down on the University of Arizona Mall in conjunction with Allison and the Lunar and Planetary Lab. So it's kind of disappointing that we weren't able to do that, but I'm glad that you guys got to see a lot of moon observing virtually last night, which was really cool. And so today we thought we'd focus on another one of our, well, actually our favorite star, the Sun. But before we get into that, just a little bit more on TAAA. I'm, like Allison said, I'm Jim Knoll. I'm the Star Party Manager for the club. We have about 400 members, and we do probably about a little over 200 events annually in a good year. Last year we did 225. And those included schools, nonprofit organizations, youth groups, public, resorts, all kinds of cool stuff. This year, obviously, we're not doing much in person, but we did have the opportunity to kind of explore and make our virtual presence a little bit more robust. So that was kind of a good thing. We've done quite a few virtual star parties, and we'll talk a little bit about that at the end. So let's take the next hour or so and talk a little bit about our Sun. So our Sun is basically just kind of an average size star, maybe a little bit smaller than most stars. There's a lot of stars out there that are much, much larger than our Sun. Some that can fit 200, 300 suns inside themselves. So they're huge. And there's also a lot of stars that are much smaller than our Sun. The predominant star in the night sky is called a red dwarf. And so they are, you know, much, much smaller than what our Sun is. When our Sun ages out, it'll become a white dwarf, is what it'll end up being. So our Sun was actually born 4.5 billion years ago. That seems like a long time, but in reality, it's only middle-aged. It's got probably another 5 billion years worth of hydrogen left in it. So what happens is, if you've ever looked to a telescope at night and you've looked at like the Orion Nebula, the Eagle Nebula, Trifid Nebula, there's lots of star-forming nebulas that you can look at in the night sky. And those are basically, and nebula means cloud, those are basically clouds of cold hydrogen gas. And so it has to be cold to be able to accrete and compress down to make stars. So that's why if you probably heard talking in the past, you probably heard talk about down in the center of like the Milky Way galaxy, and most galaxies are huge black holes, and black holes love to eat gas. Well, as they are eating that gas really gets heated up, and they don't always eat everything. It kind of spews out along the poles. But if the black hole in the center of the galaxy is actively eating, then it can actually almost turn off any star formation in and around that black hole. So it's kind of a delicate balance between the black hole surviving in the center of the galaxy, because it's necessary for us to maintain our cohesion, among other things, as a galaxy, but we don't want it to turn off star formation too much. So anyway, going back to our sun, it was born out of this huge nebula. So this nebula probably created, I don't know, hundreds of stars when it was forming 4.5 billion years ago. Most hydrogen gas clouds just kind of sit out in space. And it takes something to agitate them, something to get them going to actually start forming stars. Normally what that is maybe a nearby supernova, a star exploding. That shock wave can stir it up. Another gas clouds mixing could do that a little bit. There's lots of things that can kind of activate the cloud. And until that happens, then things just kind of sit. So it's kind of like when you're rubbing your hands and you get friction going, that starts heating things up. And same thing with like a balloon, you know, if you deflate a balloon, it will start to heat up fairly rapidly. So what happens is in this gas cloud is that the cloud starts compressing down on itself. And as it compresses more and more, it starts heating up. And about the time it gets to about 15 million degrees Fahrenheit, then that's hot enough for nuclear fusion to start within this gas cloud. And it gets big enough that the star itself that's forming would actually start pulling in material from gravity rather than just the compression coming down. So once it heats up enough to that, and then the star will continue to form, it'll get hotter and hotter. And then eventually what's left of this little solar nebula is what forms the planets and the asteroids and comets and things like that. So that's what's left over out of the material. So once the nebula is used up, what's left over is what we call an open star cluster. And we look at a lot of open star clusters through nighttime telescopes. And they're generally some of the younger stars in our galaxy, because that's what we're primarily looking at is within our galaxy. And so our sun had lots of siblings around it when it was initially formed. We are about 26,000 light years from the center of our Milky Way galaxy. So we're about halfway out on one side of the galaxy. Our galaxy, the Milky Way, is about 100 to 120,000 light years across. So we're out in the suburbs of the galaxy. And so out here, it takes us about 225 million years to make one revolution around the galaxy. So the sun's 4.5 billion years old. So we've done probably about 20 trips around the Milky Way galaxy. Well, the first couple of trips, we were probably going around the galaxy with our siblings in this little cluster. But what happens is, you know, it's kind of a loose cluster. And so eventually the outer area of stars start drifting away and gravity loses out. And then the next layer drifts out. And pretty soon, the cluster is no longer a cluster. That's why most clusters we look at in the night sky are young stars, because eventually they kind of separate out. So as that happens, then eventually, you know, we're all by ourselves. Now, about half the stars in the night sky are multiple star systems. They're 2 stars, 3, 4, 5, 6 star systems. So when these stars formed, if there were a lot of stars very close together, then they may have stayed together even after the cluster dispersed. So we're kind of unique in that we only have a single star. Our sibling, we probably had somebody close by initially, but it was not close enough to drift away. And when we look at the sun and look through the telescopes at the sun, you know, it kind of almost looks like it's a static picture, but in reality, the sun does rotate. But it rotates slowly compared to the Earth. It takes about 27 days to make one rotation. So one day on the sun is 27 Earth days long. So as we observe stuff on the sun, and we'll talk about what we're going to see, as we observe stuff on the sun, it'll slowly, if it persists for long enough of a time, it'll slowly rotate across the sky. All right, so let's take a quick look at what the inside of the sun looks like. So there's generally 3 layers of the sun. there's the core, the radiative zone, and the convection zone. Most of the action starts in the core. So in the core of our sun, it's about 27 million degrees. So the sun's kind of burst into life probably around 15 or 16 million, and it has since increased in temperature to about 27 million degrees. That's hot enough to maintain nuclear fusion. And so what's happening, the sun is made up of about 92% hydrogen and about 8% helium, and there's a little smattering of other elements in there. So what's happening in the nuclear fusion process is that hydrogen is being converted into helium. So hydrogen, the amount of hydrogen will slowly decrease and the amount of helium would increase. When that happens, it doesn't all get converted. Some of it becomes light and energy, photons of light and energy. And that's what we see in the sun. After a photon of energy starts in the sun, it bounces around through the different plasma layers and things like that. And it can take several 100,000 years for that little photon of energy to get from the center of the sun out to the edge. And then when it gets to the edge of the sun, it only takes about 8 minutes at the speed of light to get to our eyeballs. So the light you see hitting you on the surface when you're outside in the sun is roughly 200,000 years old plus 8 minutes. So it's kind of strange, you know, when we look at stuff through telescopes, we're actually looking back in time. So when we look through the telescopes today, we're going to be seeing the sun as it was 8 minutes ago. I'm going to see if Jim O'Connor wants to talk a little bit about some of the layers before I take over again, and I'll talk about some of the stuff we'll see on the surface.
Yeah, Jim, what I would bring up for everybody is the fact that when we look at the sun in a telescope, we're seeing 3 layers. We're seeing the innermost of the outer 3 layers, the photosphere, and that's what we see. The chromosphere is a layer above it, but it's a red layer, but it's so dim in the red that the chromosphere swamps it, and then the outer part is the corona. The chromosphere and the corona are only visible during eclipses. You can see those. So what we're really looking at is the chromosphere that generates the color. And the reason it can do that is that all the nuclear reaction is happening in the core, and that's a plasma soup of neutrons, protons, and electrons as a result of the creation of helium out of the hydrogen. By the time it gets out there to the point where we can see it, it's back to being hydrogen. And the reason we can see the red is because there are so many collisions up there, it's knocking electrons off, and electrons are going back on, and it gives off a red piece of light. There's other elements in there from the result of the clouds that it formed out of. So we get an image in there where with a spectrograph we can do it. The chromosphere has recently discovered seismic waves that looks like it's bringing the energy from the inner part of the sun back out to itself and the corona. That's why the chromosphere is further out than the photosphere, but the photosphere is about 10,000 degrees Fahrenheit, while the chromosphere is about 3.5 million degrees Fahrenheit, and then it gets up even hotter in the corona. And that's always been a big mystery how this is happening, and it still is. Kind of stuff is you're not going to see it with your eyeball or with the telescope, but it's interesting to see it because in your telescope it just looks like a boiling pot of oatmeal.
All right, excellent. Thanks, Jim. So quickly, what we're going to kind of see, hopefully we'll be able to see through the telescopes. Let's talk a little bit about what's on the surface. Sometimes you can see this. So sometimes out here you can see what we call flares. I don't know if you can see where my cursor is, but these generally show up as active regions or brighter regions on the surface of the sun. Flares normally are attached to the sun, but they can be pushed off of the sun. And so a lot of times you'll hear astronomers talking about the weather that's being affected, the solar weather that's being affected by Earth or coming to Earth. And solar flares can do that. And if they're bad enough and they're strong enough, they can actually become what we call coronal mass ejections, which are just huge balls of plasma gas being ejected off the sun. When a strong storm comes off the sun, if it heads towards Earth, then it'll take a day or two to get to Earth, and they'll have time to evaluate it. But it's magnetically charged material, and so as it interacts with the magnetic field of the Earth, which our magnetic field will help to disperse the solar radiation and the material around the Earth and protect us. But as it moves around, sometimes it can come back in the magnetic field lines, which are a little bit weaker on the back end, which would be the night side of the Earth. And so what's happening there is this material will travel down the magnetic field lines and interact with the poles on the North and South Pole on the Earth. And so what that ends up causing is what we call auroras, or the northern and southern lights. So generally speaking, after a lot of activity on the sun, a day or two later, we might see some activity with auroras here on Earth. If it's strong enough, because this is magnetically charged material, if it's strong enough, it can cause problems with satellites. It can cause problems with the electrical grid. So they might want to, they might watch this, and if it looks like it's going to align just right and be pretty strong, what they may do is they may selectively shut down the electrical grid on that side of the Earth where it's going to interact, isolate those huge transformers so they don't get blown, and then let the storm pass and then power back up. So you'd be down for a day or two instead of, could be months if they blow these huge transformers and have to replace them. This actually happened back in 1859. There was a huge storm that hit the Earth. And back then we had the telegraph system. And the telegraph system actually was fried because it's very electrical, magnetically evolved system. And it fried and burned up a lot of the telegraph system. And during that storm, the auroras were actually seen as far south as Cuba. So most of the time, the auroras stay in the northern or southern latitudes. But if it's a really strong storm, then they can come down. The other thing we'll see on the surface sometimes are sunspots, these little black spots on the right that you can see here. They're just slightly cooler temperature of material on the sun, and so it shows up black. They're generally about 6,500, 7,000 degrees Fahrenheit, where the surface of the sun is about 10,000. A lot of times, so it's a little more active, magnetically active area that's kind of holding the heat in and cooling down the surface. A lot of sunspots usually means there's quite a bit of activity on the sun. We probably won't see much for sunspots today because we're pretty early in the solar cycle. And then the other thing we hopefully will see a little bit of and can usually see are prominences, which is coming out here on the left side. Those are loops of gas that are usually attached to the sun, but they can get twisted. They're following the magnetic lines of the sun, but they can get twisted and break away, and that material can come towards the Earth as well. All right, so, and then real quick, well, the other thing we can see is the sun actually goes through different cycles. So this just shows the last 3 cycles, cycle 23, 24, and 25. And if you look at 23, you can see that it starts off as a minimum, and it's about an 11-year cycle from minimum to minimum. So in about 6.5 years, the sun will become a lot more active. And then another 6.5 years or so, it'll drop back down. And then some cycles are more active. You can see cycle 24 was not nearly as active as 23. It was just announced a couple weeks ago that scientists and all the data shows that we just entered solar cycle 25 in December of last year, so December of 2019. So we're really early on in this one. So we don't expect the sun to get too active. So basically in July of about 2025, that's when we're going to start seeing the peak. So as we get closer and closer to the peak, if you ever get an opportunity to look through some solar telescopes, especially some hydrogen alpha scopes, definitely do that. And then the last slide I'm going to show here before we take a look at the telescopes is the sun, what the sun looks like between a minimum and a maximum. You know, minimum, there's hardly any activity going on. Maximum, you can see lots of sunspots. Some of these smaller ones, like that one right there, or even this one, is probably about the size of the Earth. So they look small here, but you can they're pretty good size. You can put 109 Earths across the equator of the sun. 109. The whole sphere of the sun can handle 1 million Earths. That's how big it is. Of the matter in our solar system, the sun makes up 99.8% of all the matter in the solar system. Of the other 0.2%, Jupiter makes up 0.1%, and everybody else, including all the planets, asteroids, comets, everybody else is the last 0.1%. So the sun is huge. It's 93 million miles from us. We call that 1 astronomical unit. So when sometimes we talk about the distance for planets and things like that, we talk about astronomical units. All right, well, with that, I'm going to turn it over to Jim OConnor, and we'll let Jim share his screen and talk a little bit about the sun for 10 or 15 minutes, and then we'll see what Bernie's got. Bernie's got a lot of clouds. Bernie's up in Minnesota right now. He's a TAAA member, but he's up in Minnesota, so he's clouded out. But we'll see what he can see after we look at Jim's scope. So Jim, go ahead and start sharing your screen, and we'll see what you got.
Okay. The first thing I think I'll show is the scope and my setup that I'm using right now, with the exception is I'm sitting in that chair. So Bernie's in the 50, 55 degree weather there. The last I checked before I came outside, it was 92. So I am working on my forearm tans right now. And what you see there is the telescope with a lot of wires coming out of it, and a monitor by it, and then a box right in the middle. The box right in the middle is shielding a laptop computer that's sending this broadcast out to keep the temperatures down. That camera that's on the back end of that hydrogen alpha telescope, it's only looking at one frequency with a little bit of space around that frequency in a special set of crystals on the inside. It sends a signal out, and I'm grabbing it with a camera instead of an eyepiece. It's got two video lines, one to go to the monitor, one go to the computer. It's got a control line. If you look at the picture of the blue box on the table, that little silver box is connected to the back of the camera, so I can make changes in the camera. It's also got 4 lines going in, one for the telescope, the camera itself, and one for the cooling fans that are around it to keep the temperature cool. Now, we don't have to do that today. This is mostly for long duration pictures at night if I'm going hot enough to heat up the video chip. So I really don't need the cooler. And on the table next to my 2 spare sets of video cables in case mine happen to have it right now. But I'm in that white chair staring into that blue box trying to see what I can show you. The next thing I'll shift to, if I can make the shifting thing work, is what I'm showing itself. I knew you could do this. There it goes. And there's the sun right now. Now it's drifted a little bit over, and here is one of those curses of being a solar astronomer at random locations. I'm going to center it up. I don't get Polaris in the morning when I set this thing up, so I've got to have a good guess, which I did because I got the sun, but it ended up being a little bit wrong in one axis or the other, and I'm going to pull
Jim,
it over there, and you'll notice how
we don't see your telescope view yet, so maybe it's a little lag on the switch.
Yeah, what
it
you may
could
have
be.
to do.
Let me get it over there. I know when
Okay.
you spotlighted me, it was,
Okay, let me make sure.
What you may need to do, Jim, is just go up to the top of where your viewing is and just select
stop and
a
start.
new view. Yeah, or you can stop and start it. Just do a new share, and then select the telescope view.
Okay, I'm going to stop and then reselect. And screen share. There we are.
I'm still jealous of Bernie's jacket.
Me too.
Seeing this jacket on screen.
I'm not jealous of anybody's jacket. I'm jealous of Bernie's weather. Okay, have you got
true.
anything yet?
It's trying, yeah. There it is. Thank you.
Yeah, I should have a reddish orange basketball. And that the reason you get our eyes down here see a white or whitish yellow sun, that's because of the blue scattering in the sky. The sun itself, when you're out, is white if you're out in space because it's got all of the visible frequencies together. But this the telescope I'm using happens to look for only one wavelength, the wavelength of ionized hydrogen. And that's what I'm showing right there. And if you look, it's such a pristine, nice, smooth ball because this is the bottom of the beginning of cycle number 25. And it hasn't decided to get very active yet. But like I said, it can look like a bowl of oatmeal. You can see some granulation on it. So what I'm going to do is I'm going to change the image a little bit, and you'll see some, I'm hoping you'll see some, those are controls of the camera. And what I'm going to do is control the shutter speed on the camera. Right now, the shutter speed is 1/12,000th of a second. And when I get up there to the level control, I'm going to drop it significantly. And what's going to happen, that's the shutter speed, 1/8,000th, 3,000th. Notice it's swamping now, everything. If there are any prominences that might be active, they might pop up. Now this morning I had one on the left hand. Can you see a little feather there right about the 9 o'clock? That's about all the sun's doing right now, and some stuff on the bottom. So I'm going to do another trick. And this is where you get to peek behind the magician's curtain. I will go to the zoom. And I will turn the zoom on, if I can handle the screen delay and what it's telling me what's going on. There it goes. And now let's try to get that plot over into the screen. And there it is. If you can see that little tail sitting over there down under the word zoom, and I'm going to get rid of that. I'm going to go back up to the level control because I want to play with that brightness a little bit. And boy, it's really, I've got ADD, so I'm very into it, goes way too far. Let's see if I can get to ALC calmly. There's level. I'm at 1/350th of a second. Let me get down to about 1/250th and then 1/50th. Or about 1/80th of a second. Maybe we can see a little more. I'm not sure. And get all this junk off the screen. And down around, it's not really quite 3 o'clock, but down below it, as the upper atmospheric turbulence that I'm picking up now because of the longer time, you can see a little feather sticking up there, or it might be a bush there. That is all the sun's giving us right now, with one exception. What I've done is I've swamped the video chip in the camera with light. And when I do that, it starts looking for anything that it can contrast to. And what it sees is that dim hydrogen prominence coming out. What I'm going to, now remember, this camera can be a 360-degree circle. So just because I see it here doesn't mean you'll see it anywhere else. I'm going to move it over. I'm going to move the image over. And look at the very bottom, because at the 6 o'clock position this morning at about 8:30, I thought I saw something. Yes, I know you can move. There you go. And as it moves, sometimes you can see that feather jump out. And my monitor display isn't as good sometimes as what comes out on the broadcast. So if anybody sees any other kind of things jumping out, especially Bernie and Jim, who know some of this stuff even better than I
Yeah, Jim, we're still looking at
do.
the left
And what's
side of the
happening,
sun.
come on, I know. Yeah, I was looking
There
at the
it
left
goes.
side, the 3 o'clock position. Now I've lost it intentionally. And now I'm going to try to bring it up to look down at the bottom and see if we got anything. And what I saw this morning was an awful lot of surface activity, but no great jump outs, which was really funny because it looked like wind was blowing around. And done. It's not a camera artifact. That's actually weird things going on the surface of the sun in that spot. And unfortunately, I'm trying not to overshoot it. And you see all that activity down around 6 to 5 o'clock. There is some moderate amount of activity there on that part of the sun. And that is the beginnings of what it's going to take because to get a really good view, because we finally, about 2 weeks ago, I believe, got the magnetic fields of the sun to finally align for the cycle. Every solar cycle switches magnetic poles. And for a while, it's all chaotic as far as the poles are concerned. So they don't have a chance to gang up together and show a feature. And I'm moving this over a little bit so you can see what's going on there on that edge of the sun. Now, I don't know what's top and bottom on the sun. This is just what the camera sees as top and bottom. If I can get it to move.
Yeah, and unfortunately, Jim, I'm not seeing a lot of detail coming off.
You won't. It'll be like almost like raster lines jumping along the bottom part and then up towards the 5 o'clock, 4 o'clock, up towards the right. There is a little bit of activity, like a set of hills or a ridge. Those are all active areas, but they're minorly active. They're not a nice smooth curve like the top of the sun was. So bottom line is we don't have a whole heck of a lot going on. So what I'm going to do is I'm going to turn off, what I'm going to do is try to center it back up and turn off that zoom and all the color stuff. Let's see, the first thing I'll do is turn off the zoom so I can see what I'm doing here and do it slowly. I was up at 1.8, my zoom was 1.8 because that was about the most I could do. Like you can see that little box and I'm turning it off. Turn off. There. Let's get us back down if we can. And back up a bit. And now I'm going to take level control, the shutter speed, and get it back to 1/12,000th of a second so we can see what the sun is really looking like. If I can have enough patience to let that arrow move. So right now, I'm probably about 1/180th of a second. So I'm going to go completely through off and to 12, it'll jump to 1/12,000th of a second. There's back to being the sun with no discernible features on the surface with this style telescope. This telescope is similar to the same kinds of telescope that Jim Knoll and Bernie Stinger have. It's a 60 millimeter, except mine has got an internal etalon on it, but I've got the same kind of blocking filter they do, called a B1200, which means it's got 12 millimeters of aperture that gets to the camera. So that's pretty much what I can see, and I'm guessing that's about all that Jim and Bernie could pull in too. Now I'm going to get this junk off the screen for now. And the reason you see it lag somewhat is I've got it actually stacking 4 images to move those out. And the reason is that the atmosphere is pretty turbulent right now, and to smooth out some of the rumbles, I'm actually at 1/12,000th of a second frames to get to that image. Okay, that's the sun. And the sun over history has been very important to people. And different peoples, different cultures handle the sun in different ways. One of the most clever groups was back around maybe 2,300 years ago, the Caledonians near northern Iraq. They were smart enough to know that at night, the constellations kept moving into the daytime. So they knew where the sun was in a particular constellation that would be behind it, but it was too bright to see. Well, what they did was they started a way of measuring roughly monthly cycles of how the sun was doing. That was the beginning of what we now call the zodiac. But that was not used for what we use the zodiac now. That was only used to predict municipal actions and military actions. The Greeks found out about it because they're communicating all around the eastern band of the Mediterranean, and they went a little more broad in their appreciation of what the sun was doing in what constellation, plus the other celestial objects, like the planets and the moon. And that's when zodiacal predictions became common. So that in the case of the Caledonians, they cared about where the sun was only because of how they were going to run their social lives, but the Greeks did it for all life, all decisions and operations and predictions for what they did. So they did the sun and were pretty, they were pretty interested in it. But what they didn't know is when they created this thing, for them, Zodiacos was something pertaining to the sun on a regular basis. And they had a word in Greek that doesn't have a soft C sound called kyklos, like we would say cycle. Kyklos meant something periodic. So they had a term, Zodiacos kyklos, which was a moving sun through living things. The living things were their names of the constellation. The name of the constellations that they were in turned out to get labels onto the month. Well, what they didn't know that this had been done for over 1,000 years before, but not with the sun in the sky. It was done with trees. The Celtic peoples started out in the barbarians pressured them to move, and they kept moving across northern Europe and ended up in the British Isles over a millennia or so moving. Well, what ended up happening is they had a zodiac, but the zodiac signs were based on what trees or flowering entities that were strongest in that month or most robust. And so in the month of December, they had the fir tree. That was their symbol of December. When the Romans came into the British Isles and started to conquer the Celts, they noticed that symbol that was there because the Celts had the fir as being important because it seemed to live through the winter inside their dwellings because they thought it brought life with them during the middle of winter. Well, the Romans started to take note of this, especially after about 300 AD or so, when Christianity started to take over. When Christianity took over, they noticed that the Romans had a feast of Saturnalia in December, so they made that Christmas, the birth of Christ, that had happened to take over the feast of Saturnalia, and that's how we got the Christmas tree, was sharing among the cultures. So that's kind of a long-winded way of saying we get Christmas trees because the Celts like the firs because they seem to be alive, and they wanted something to mark each month.
Hey, Jim.
Yeah.
We probably need to wrap up so we can get Bernie in. We're coming up on 45 minutes, so we just have a few minutes left.
Okay, the last thing I'll talk about is Native Americans have lots of cultures about that. One I will talk about, and that's the Yaqui. The Yaqui had a special cultural under our cultural appreciation of the sun and the moon. They thought that the earth was created by the sun and the moon, even though they're not, the sun and the moon are not related. But the sun wanted the moon to be his girlfriend. The moon was not too cool about that. So she said, if you bring me the best gift possible, I might consider being associated with you. So the sun went out and tried to find something. Comes back in 30 days when he's close to the moon and doesn't fit. It's not the right thing. So she says, nope. And so the moon runs away from him. Ever since then, the sun has been trying to find the right thing so the moon will stick with him and be his bride. But the moon says no and runs away. But halfway through the month, when it's a full moon, she says, okay, let me go back and see what this guy's come up with this time. So that's how we get the lunar cycle, and it's a Yaqui cultural lore of how the sky works. And Bernie, what you got?
Okay, my turn, I guess, huh?
I guess.
I think you have to drop your share, Jim.
I'm trying to.
And we do have a question while we're doing our transition. We would like to see the Aurora Borealis. Any advice?
Bernie, you should probably answer that
Yes.
because you're in the neck of the woods of
Right.
being able to see it.
Well, the Aurora Borealis, and I believe there has been some sun activity recently that might spur some out there. I know, talking to a couple of friends recently, they have actually been able to detect some Aurora Borealis up in the northern part of the state. I'm currently up in Minnesota right now. And to see Aurora Borealis, typically the further north you are, the better. So in my case, in Minnesota, even from lower Minnesota, where I'm at, in the Minneapolis area right now, to see the Aurora Borealis, I would probably drive north to a darker location and try to view it there. And I don't know where the person is located that asked that question. If you're down in the southern states, you probably don't have much of a chance. It's rare for the Aurora Borealis to go any further south than, maybe 40 degrees north latitude. So typically along the northern tier states is where the aurora shows up. Or if you're very fortunate and you live in Canada or up in Alaska, then you can see it far, far easier. So that would be the situation. And if you're down south, get on a plane and head north. That's about the only way you're going to pull it off. Okay.
Bernie, I'd like to throw in one little
Okay, Jim, go ahead.
thing. The auroras happen because of the solar wind. And the solar wind has charged particles. And when it comes off the corona, if there's a mass ejection of material out of the corona, then they have plus charges and minus charges in those elements that are coming out. They hit the Earth's magnetic field. So the negative particles get directed to the North Pole, the North Magnetic Pole. The positive charges get directed towards the South Magnetic Pole. So once in a while, if you pay attention to certain scientific websites, you get notices of coronal mass ejections or geomagnetic storms. That's when those elements hit the magnetic fields and you get the South has an aurora also. It's called the Aurora Australis. And so the Aurora Borealis and the Aurora Australis are the result of charged particles re-entering the atmosphere.
Okay, thank you, Jim. So what I'm going to show you, being up in Minnesota, is unfortunately what I see on a cloudy day when I try to look at the sun. So here's my my current image of the sun, and as you can probably tell, it is one big yellow fuzzball with no detail. Unfortunately, it's been like that pretty much all day. You can see, if you look closely, you probably saw a cloud pass by in front of it. There's an overcast haze. So that is unfortunately what I'm seeing as sun right now. So what I'd like to do is turn the share off here for a second. I'm going to show you my setup, and now you should be seeing an image of my telescope and how I normally have it set up. This was taken a couple days ago when I had a little more sunlight available. But as you can see here, I've got a what's called a Celestron motorized mount. This allows you to lock onto and stay with an object once you tell the mount to lock onto a given object, in this case, the sun. Up above, this white tube is a 60 millimeter solar scope. It's made by Lunt out of Tucson, Arizona. And within that solar scope, right about this location here, is what's called the Etalon. That is a filter that's designed to filter out all of the dangerous sunlight, if you will, and leave you with just 1 angstrom of electromagnetic bandwidth, to get technical on you. And that angstrom of bandwidth, if you center it on what's called the hydrogen alpha line, you're then magically able to see prominences coming off of the sun. So that's the trick, is to center that bandwidth, that pass band, right on that hydrogen alpha line. And to do that, it's if you see this little cord coming down, that's actually a pressure cord coming down to this instrument right here, down on the table, which is creating a pressure on this passband filter. And by varying the pressure, I can change the frequency of that passband. So it's a little trick. And then to control that controller, this USB cable is coming back to my PC. So I've got a little control here on my PC to affect that passband. And then on the very back end is an astronomical camera that is taking an image, the live image, and feeding it back on USB back into the house here, where I can then look at it on my screen. So that's what the setup looks like. And to go back again, just to show you very quickly, here is what the camera is seeing right now, which unfortunately is not much in the way of prominences. So what I'm going to do, go back to my images there and show you some images that I've taken in the last few days. So here's an example of a good sunny day. This was about 3 days ago. I took this image from that same setup that I just showed you, showing the sun and some nice prominences jumping off of the sun. So here's a very good example of what you typically see with this type of telescope on a good sunny day with no clouds, and the prominences are leaping off of the solar surface. There's also a few on the other side over here. This particular one I like the best because it looks like a little pillar and a wedge-shaped artifact there on the prominence as well. Let me show you another one. Now here's an image of the sun but I backed off on the exposure so that you can see more of the surface details. So you notice the prominences now have kind of vanished, but the surface of the sun is more obvious. And if you look closely on the surface, you'll notice the surface is kind of pockmarked, like it's zillions of little pimples all over the surface of the sun. Those are specules, or boiling pockets of hot gas, hot plasma that's coming to the surface on the sun. And it's like a boiling pot of hot water. That's the easiest way to describe it. If you bring a pot of hot water to a boil, you'll see all these bubbling hot spots popping up to the surface. And that's exactly what the sun is doing here too. It's churning up this hot plasma that's coming to the surface. Now let's take a look at another image.
Hey, Bernie, we question about these prominences. What is the rough scale height? We see these jetting off the edge. What would be a rough kind of idea of the height of those? Yeah.
Okay, well, here's an example of one. I'm going to bring it up into view here. This one is, I would estimate this one as probably 10,000 miles. Maybe between 10 and 20,000 miles high. So this is larger than the Earth. If you can put a shape here of the Earth, that would be larger than the Earth. That's how large these prominences are. And
wow,
these are average. This image was taken about 4 years ago, with this same setup that I'm showing you. This image was taken during the solar maximum. So in this case, you see there's not only prominences, but also a lot of activity on the surface of the sun itself. These are sunspots, but in hydrogen alpha, rather than showing as black areas, they're actually brighter areas because they're hot areas of hot hydrogen gas. This is very typical of sunspots in hydrogen alpha light. And you'll also notice right here, this is a very interesting feature here. This is called a filament. Notice it has kind of a line shape. And what you're actually looking at there is a prominence, but because the prominence is towards us rather than on the edge, it's leaping off the sun towards us. So we don't see this arc of light. What we see is the arc, but because it's coming towards us, it looks more like a line. So if you can think of this as a prominence, but it's leaping upwards towards us. Now, sometimes these prominences have enough energy to actually leap off the surface. So instead of being connected to the surface like this one, they can actually leap off the surface. This happens when there's a disconnect. In other words, the hot plasma from the sun, the hot hydrogen gas, has followed the magnetic field line that it was anchored to up into space. And when the magnetic field line falls away, that hot plasma has an option of either falling back to the sun's surface if there's enough gravity to pull it back down again, or continuing on off into space, in which case you end up with a solar flare. Now, that flare going off into space typically will just go off and not harm anything or affect anything. But if it's aimed at the Earth, it takes about 2 days to get here. And if it's aimed at the Earth, it will hit the Earth and disrupt our ionosphere. It will disrupt communications on satellites. It can mess up the electrical grid, depending on how powerful it is. So this is the kind of thing that they watch for. And fortunately, it takes a couple days typically to reach us. So we have enough time to prepare and get ready for it as much as we possibly can.
Question sort of related back to our first question of the Aurora Borealis. Is this the type of solar activity that we want, or is there a more specific type of solar flare that we would say, you know, catches the magnetic field a little more?
Well, the more powerful the flare off the sun, the more Aurora Borealis you're going to get if it's aimed towards us. So a minor one, something like this, isn't going to accomplish much. It might cause a little reddish or greenish glow in the sky. But a very powerful one that was maybe 10 times this size, could cause some very beautiful aurora. This time of year, aurora is difficult because we're at the not this time of year, but at this point in the sunspot minimum, we don't get much aurora because the amount of flaring is very minimal. It's usually around sunspot maximum when the bigger, huge flares occur. Not always, but that's typically when they happen. Powerful ones that will then give us far greater aurora borealis and aurora australis, as Jim pointed out, that they also occur on the southern hemisphere. Now, here's a little video of a nice aurora a nice sunspot that was present a couple of years ago that caused a nice flare to occur. Now this one was pointed downwards, so it didn't come towards the Earth. Just to give you a little idea of another flare. And I'm going to finish up with this image, which is one I took at the solar eclipse that happened back in 2017. Those of you who were fortunate enough to see the solar eclipse, you will probably remember that there were a few flares along the edge. And with this type of telescope, you can not only see the flares during the total eclipse phase, but also prior to this total eclipse. So this is the solar eclipse almost about to happen within about 15 minutes of it occurring, but I was already capturing the solar prominences that were going to be more obvious once the sun got totally covered. So I think we've used up our hours. So I'm going to stop my share, and thank you very much for your time.
Yes, thank you, Bernie. Thank you, Jim. Thank you, Jim. All of TAAA for always being present for both the Tucson community and, of course, now your virtual reach. And I will say that we'll be teaming up with TAAA for our closing events, since the art galleries that are available on our Art of Planetary Science 2020 page are open until October 31st. We kind of want to remind everyone and come back together towards the end of it. So on October 24th, a week before we close out the art show, we will be inviting TAAA back for an evening telescope viewing, similar to what you saw here, actually looking through these telescopes set up in various locations. And I think we've got mapped out for that night, like a decent part of the solar system. I think we've got the moon, we've got Mars. It's a first quarter moon. That's actually what TAAA really honed in on. It was this really nice moon phase for you guys to view. So first quarter moon, Mars, Jupiter, Saturn, and then at the end of the night, I think we've got Uranus and Neptune, and so a
Yeah.
full suite of the solar system.
Yeah, absolutely. That'll be a lot of fun. So that's going to be October 24th, and we're looking forward to showing off the solar system. Yeah.
Yeah, that's we're really looking forward to that, and we'll also bring Flandro in. So we had a little bit of virtual Flandro this weekend, and so we'll have TAAA live telescopes, and we'll have the Flandro Science Center with a spooky Halloween constellation tour. So with that, we thank TAAA again, and we'll see you October 24.
All right. Sounds good. Thanks, Allison.
All right, bye.
Thank you. Bye.
All right. All right. Thank you, everyone, for kicking off our Sunday with, of course, actually viewing the sun, a little bit of a